This screencast covers slides 18 through 23 in the version of the Thermo PowerPoint dated January 28, 2016. This is the third segment looking at different kinds of energy so we can understand in detail the underpinnings of the first law of thermodynamics. So now we're going to talk about, this section is going to talk about electrostatic potential energy. Will be the central focus. The specific manifestations of that that happen in molecular atomic physics and in biochemistry. One thing in the background, well, one thing that we will discuss is something called the dielectric constant. Now, dielectric constant plays a fundamental role in electrostatic theory and applications. It is also related to something called a dipole moment. You've probably heard about dipole moments. I'm not sure how much they've been explained to you in terms of their details nor their relationship to the thing called the dielectric constant. Dipole moments are really a fundamentally important thing in physical chemistry and applied physical chemistry. And so we will get our first sort of taste of them in the course of this Thermo module. So you've almost all certainly at some point in the past seen Coulomb's law. It is an inverse square law. It says that the electrostatic force between two charges, Q1 and Q2, is equal to the product of the charges divided by the square of the distance between the charges times epsilon, and epsilon is the dielectric constant. More about that very shortly. The direction of the force follows the vector between the two charges, and so the force is essentially collinear with the vector separating them. And so this is something you've almost certainly seen before. One of the things we're going to do momentarily is derive the expression for the electrostatic potential energy, which you've also almost certainly seen before. We're going to do it in a way that emphasizes, again, this definition of work as work being force times distance over which it's applied, and this being sort of the unifying point between all kinds of energy and the specific sort of relationship that effectively determines the conservation of energy. Right? So any time that a force is exerted, if applied over a certain distance, work is done. That work will be equal to the change in the energy of the object, the system. And the only way you remove energy of the system is by having it do work on something else. And so that's going to be front and center here as we discussed electrostatic forces and potential energy. All right. So again, epsilon is the dielectric constant. What is this all about? Well, you can see from the function here, from the force expression, that epsilon is in the denominator. That means large epsilon attenuates electrostatic force compared to small epsilon. Now, epsilon in a vacuum is 1. And so you may have, that's why this can be ignored if you're looking at electrostatic forces in a vacuum. And so many treatments of electrostatics will start in the vacuum situation. And, again, in a vacuum, epsilon is equal to 1. Air is something pretty, the dielectric constant isn't exactly 1, but it's pretty close. So you can also do electrostatics, in air and sort of ignore the dielectric constant. But the dielectric constant, as we'll see momentarily in water, is 80. And so that means that the electrostatic force is effectively 80-fold lower in water. Now, where this comes from and its origin and its implications are both hugely important in terms of biophysical chemistry, which is one of the reasons we're treating this today. So this is, now what has just appeared here is supposed to schematize the major contribution to the dielectric constant that you find in water. And so this is supposed to represent, these little ovals are with pluses and minuses, these are supposed to represent dipoles. A dipole, we'll talk about this in much greater detail later on, at least in my undergraduate biophysics class, because dipoles play a fundamentally important role in spectroscopy and other aspects of physical chemistry. A dipole, you've probably heard a little bit about this, a dipole is a separation of charges. And so in my undergraduate physical chemistry class, we will, within about 6 or 8 weeks, we will go through something called a multipole expansion, which is a very elegant way to simplify analysis of how charge distributions interact. Of course, in molecules, you have charge distributions. The dipole in the simplest case involves two equal but opposite charges that have some special spatial separation between them. And so this kind of molecular dipole approximates, for instance, the properties of a water molecule. In water, you have a positive charge on the proton and on the two protons, and a partial positive charge on the protons of about roughly +1/2 each, and a negative charge on the oxygen. The center of mass of the positive charge is separated from the negative charge, and that charge separation of the water molecule can be modeled to behave as a dipole. Now, what this is supposed to schematize is what happens to the orientation of dipoles, for instance, water molecules, when charged particles are immersed in, let's say, water. What will happen is, let's say that Q1 is a negative charge. The dipoles, the water molecules will tend to reorient themselves so that the positive end of the water molecules, the part with the end with the protons, becomes closer to the negative charge. It will tend to do that because, of course, positive charge is attracted to negative charge. If you put a water molecule in random orientation between these two charges, the positive end of the water molecule, let's say Q1, is negatively charged. So let's say this, the way this is schematized here, it would assume that the Q1 charge is negative. So we're going to say that this is roughly a negative charge. As it's schematized here, that would be a negative charge. And then this would be a positive charge. So in this circumstance, if we put these two charges, let's say, into and somehow hold them still in some bath of water, the positive ends of the water molecules will tend to rotate towards the negative charge. They will be attracted towards it. There will be a force, and they will tend to rotate. We'll talk more about that very shortly. The negative end, in contrast,
it's 7:30.
Of course, be pulled. Well, there will be a force attracting it to the positive charge, and it will rotate in that direction. And so the water will tend to produce an alignment of these dipoles with their positive ends towards negative charge and the negative ends towards the positive charge. Now, what this does, because these dipoles now have their own electric field, it tends to attenuate the electric charge effectively. Right? So here, all the positive, as the water molecules align their dipoles, the positive ends tend to move closer to the negative charge. So that will produce a net accumulation of positive charge down here, and a net accumulation of negative charge down here. And that will, of course, tend to cancel out the charges that are causing the alignment. And so that cancellation effect is an attenuation, and that attenuation is described by the dielectric constant. Now, if you were to try to break down the physics and mechanics and dynamics of this in some exact manner, it would become very complicated very quickly. Well, that's the elegance of this kind of physical chemical theory, that you take a very complicated process, having water molecules align themselves as they're acted on by positive and negative charges. You take an exceedingly complicated process and you convert it to a simple scalar constant. So as I told you before, the dielectric constant for water is about 80. We'll talk a little bit more about dielectric constants in different media in a minute. In water, it's 80. And so you put two charges in water, and the force between them is attenuated 80-fold compared to what the force would be between them in vacuum. The cause of that is this very complicated molecular orientation process. If we were to go into this detail, we'd actually see that there is a balance between the loss of order of the water upon orientation in the gain in enthalpy of the water charge interactions with the fixed charges. Again, this is thermodynamically and physically a rather complicated process, but that's reduced to a simple scalar constant of 80. So that's actually quite powerful, quite elegant. We'll try to understand more about that later. Okay, so what we want to do for the moment is consider what kind of work is done in bringing these charges into this kind of separation. And this is ultimately the origin of the what you've been told is electrostatic potential energy, right? So if we start, the model we start with is having the two charges Q1 and Q2 infinitely far apart. When the charges are infinitely far apart, they are basically not interacting energetically. And then we consider what happens as you let charge 2 move under the influence of the, let's say in this case, we're letting charge 2 move under the influence of the electrostatic force between them. So we're going to take charge Q2, start it infinitely far away from Q1, and then we're going to let the electrostatic force bring them together. Sorry about that. And we're going to consider what kind of work was done by the electrostatic force in bringing them to this separation of X final. Okay, so the force it is being exerted on Q2 in this coordinate system is negative Q1, Q2, epsilon, again, the dielectric constant. Sorry about the flitting of the mouse. It's Q1, Q2, epsilon over x squared, where x squared is the distance between them at some point in this trajectory. With the unit vector that just points between the two charges. Okay, so the product of the charges divided by epsilon, the dielectric constant, times the square of the distance between them. So that's the force. When we let the electrostatic force between them move Q2 closer to Q1, right? And so in this coordinate system, the force is negative, right? The force is, we'll say the coordinate, this would be the positive direction going from, let me draw that quickly. The positive direction in this coordinate system would be, let's say, here. And that means because the force is now going instead in this direction, that means that the force between them is negative in this coordinate system. So we take that negative force and integrate it over the distance over which it's applied. Ultimately, that distance will go in infinitesimal increments from infinity down to x final. And so we take this path integral. We use our physics definition of work, force times the distance over which it's applied. In this case, the direction over which we are applying the force is collinear with the vector describing the force. So once again, the vectorial quantities drop out. Q1 and Q2 are constants. And so we end up with Q1, Q2, epsilon in a given medium. Water is a constant, it's 80. And so we end up with negative 1 over x squared dx. Well, you very likely remember that the integral of negative 1 over x squared is positive 1 over x. The reason for that is 1 over x is x to the negative 1. We take the derivative of that and we get negative 1 over x to the negative 2. So this, again, the integral has to be the antiderivative, which means if we differentiate this, we should get that, which we do. And so then we will take the integral from infinity to x final. 1 over infinity is 0, so we ignore that. So we get the work done in bringing these two charges from infinite separation to a separation of x final is Q1, Q2, epsilon, x final. So you folks will probably all recognize this as what you have been told in the past was the electrostatic potential energy. I suspect this one you've actually seen the derivation of before. When we derive the kinetic energy, the calculus underlying that is ever so slightly more complicated, so that often is just sort of presented as a fact. It's not exactly a fact, right? It actually stems from a more basic principle defining work. And establishing the relationship between work and energy. So we apply those definition and work through the math, and we get that the work done in bringing the Q1 and Q2 together from infinite separation to a distance of x final is Q1 Q2 over epsilon x final. This is what you've been seen has been explained to you before as the electrostatic potential energy. And so what do we see? We see the electrostatic potential energy is exactly equal to the work that was done by the electric force in bringing these two charges together. So that is the meaning of the electrostatic potential energy. It shows that the exact connection between electrostatic potential energy and the overall conservation of energy. And again, the conservation of energy works through this relationship where energy is only changed by work. Work involves applying a force over a distance. The amount of work that you do is exactly equal to the change in the energy. In this case, this work is exactly equal to the change in electrostatic potential energy. So of course, if we did this experiment, let's say in a vacuum to begin with, that point epsilon would be 1. We take Q2 infinitely far away from Q1. But the electrostatic force pulls them together. Well, of course, while they're being pulled together, if they're being pulled together without any other forces acting on them, Q2 would accelerate, right? As it accelerates, it would gain kinetic energy. What this is, in that case, the kinetic energy that was gained by Q2 would be exactly equal to Q1, Q2 over epsilon x final. And so basically, effectively the loss of electrostatic potential energy in this system would be exactly equal to the gain in the kinetic energy as these things came together, right? So if this charge were not fixed in some way or held down in some way, in the electrostatic force between the charges were just pulling them together, they would be accelerated. This would gain kinetic energy. It would gain exactly that much kinetic energy. And so this is an example of how you have an exact trade-off. It's an example of how energy is conserved. The change in electrostatic potential energy has to be exactly equal to the gain in kinetic energy. At that point, if we wanted to now slow it down and fix the charge at this point in phase space, we would have to decelerate it, and we'd have to do work to do that, and that work would be going into some other kind of energy. But here we see how there are these precise transactions where work is done that moves energy from one storage point, storage location to another. Okay, so again, the work done in bringing these things to this exact separation of x final, Q1, Q2 over epsilon x final. We have to do a sign check. Does this make sense? This is saying that the work in this case is the positive Q1, Q2, but of course if Q1 and Q2 are in opposite signs, that means the amount of work done is negative. And that means if the work is positive, that means energy was input into the system. When we looked at kinetic energy, when we did work accelerating it, we did positive work, and that positive work produced the kinetic energy. In this case, we would be getting negative work. What does that mean? Well, that means that there was basically a greater amount of electrostatic potential energy when these things were far apart. An easy way to see that is if you started with Q1 and Q2 at this separation and you pushed them infinitely far apart, well, you'd have to put energy in. You'd have to do work, put energy in to push them apart. When you release them and they come together, then energy is released. As I said before, if you were to do this sort of in vacuum and release the two particles, they would, let's say for whatever reason, by whatever connivance, Q1 is fixed in space, Q2 would accelerate towards it. By the time it hit this point, it would gain exactly how much, it would gain kinetic energy exactly equal to negative to Q1, Q2 over epsilon x final. It's the gain in kinetic energy would exactly equal to the basically reduction in electrostatic potential energy. And so this is an important example for many reasons. It shows the exact balance between work and energy. It shows another specific example of exactly how and why energy is conserved. And it is also incredibly important in terms of us understanding the details of molecular interactions, either in a vacuum or in solution, where those interactions are attenuated by the dielectric constant. So let's summarize. This is yet another example of the first law in its nitty-gritty details and in action. Heat is work. Again, sort of classical mechanical or quantum mechanical energy. In solution thermodynamics, we call that kind of energy enthalpy, to distinguish it from free energy, which we will see in due course is something very, very different. This kind of enthalpy is called electrostatic potential energy. And again, the dielectric constant is an incredibly important factor in living systems, in material science, in many different areas of physics, but in particular for the evolution and biochemical function and biophysical analysis of proteins and of living systems. Life is a water-based phenomenon, at least as we know it here on Earth. The epsilon for water is 80. That's because it has water molecules has a very strong molecular dipole. One way to get a high dielectric constant is to have a strong molecular dipole that is free to rearrange itself in an electrostatic field and thereby form a charge distribution that tends to offset or attenuate that electric field, and then the dielectric constant on the whole is an attenuator of electrostatic force and therefore also of electrostatic potential energy. So epsilon for water is 80. Again, this reflects some very, very clever physical reasoning and thinking and physical chemistry that has been done over the course of many, many, many years. That takes a complicated process of dipolar rearrangement under the force of an electric field, and it reduces that exceedingly complicated physical process to a simple scalar that is a characteristic of a medium, and the value of the dielectric constant for water is again about 80. Okay, so apolar solvents, something like, let's say, as an example, ethanol, they will have much lower dielectric constants, 2 to 8. They won't necessarily be 1 for several reasons. For one thing, ethanol, for instance, does have a dipole, a fixed dipole, because the OH group is a polar entity. It's not anywhere near as strong a dipole as that is water, but it does have a molecular dipole. But there's another contribution to dielectric constant, which is polarizability. As we're going to see shortly when we talk about the van der Waals force, electron clouds on atoms are polarizable. The polarizable electron clouds can also, another sort of way that you could get this kind of compensating charge distribution is through just having a polarizable species. If you put a polarizable atom here that had no dipole moment, the electric field would tend to move the electrons around and induce a dipole, and so polarizable species will have induced dipoles. And therefore, even very apolar materials, even materials with really no net dielectric constant, benzene, for instance, has no net dielectric no net dipole. Benzene has no net dipole, but it is polarizable, and so it does have a dielectric constant significantly greater than 1, nowhere near as great as that as water. Now, when we talk about proteins later on, many people, of course, try to model and understand the physical chemistry of proteins. It turns out in the protein interior, because it's made of mostly apolar species, phenylalanine side chains, that's benzene, leucine, that's an aliphatic. In the interior of a protein, many people model that as having an approximate dielectric constant of 2 to 8, which is roughly matching that of an apolar solvent. And so a reasonable value for the protein interior is about 4, which again is in the range for apolar solvents. So again, net take-home message, the dielectric constant is an attenuator of the electrostatic force, and the electrostatic interaction strength, electrostatic potential energy, is very, very strongly modulated by the dielectric constant. Now, at this point, we can go on and think about electrostatic interactions in some more detail, and particular kinds of electrostatic interactions that are common and important in biochemical systems, in water. Again, life is a water-based phenomenon. And so one important kind of electrostatic interaction is something called a hydrogen bond. You've almost certainly heard of this before. People will still argue whether some hydrogen bonds have some quantum mechanical characteristics to them, but everyone would agree that the vast majority, 99 to 99.99% of all hydrogen bonds in biochemical systems, in living organisms, 99+% of all hydrogen bonds are really just electrostatic interactions. And so, of course, the electrostatic force is inversely proportional to distance. To the square of distance, electrostatic potential energy is inversely proportional to the first power of distance. The reason hydrogen bonds are notable and important in biology is that the proton is very small. Because the proton is very small, the distance between the proton and a oppositely charged, let's say, oxygen atom is very small. Because that separation distance is small, the electrostatic force between them is very small. That's why hydrogen bonds are energetically important in biological systems, biochemical systems, because the proton being small allows negatively charged atoms to approach it very closely. That produces a strong Coulombic interaction between them. The term Coulombic, of course, comes from Coulomb's law. The last couple slides, derived effectively, used Coulomb's law to derive the expression for the electrostatic potential energy, so we could see how electrostatic potential energy related to the first law of thermodynamics. Hydrogen bonds represent a common and important kind of electrostatic interaction in biological biochemical systems. So this is providing an example of a water molecule, hydrogen bonding with a carbonyl group. Carbonyl groups are found in many, many different kinds of organic chemicals, and of course they're also found in proteins. In the protein, of course, the most commonly occurring carbonyl group is the one in the amide bond. If this carbonyl group were in an amide bond, it would have about a +1/2 positive charge on the carbon and a -1/2 negative charge on the oxygen. In water, we have approximately a +1/2 positive charge on the proton and approximately -1 charge on the oxygen. Here we're showing one hydrogen atom hydrogen bonding to the carbonyl group. How does this relate to the dipole moment? Interesting question. Well, the dipole moment goes from the negative end, as we'll see later, especially when we talk about spectroscopy. The dipole moment is represented often as an arrow with a cross at one end. The arrow, by convention, is the positive end. The cross is at the negative end. In this case, the dipole moment would point towards sort of the mean, the geometric mean position between the two hydrogen, the center of mass, effectively, of the two hydrogen atoms. And so the molecular dipole moment of water would be pointing in this direction. But the hydrogen bond is strongest when a hydrogen atom with its positive charge becomes as close as possible to the oxygen atom. So again, this is a common interaction, an important interaction for biological systems. It is, again, very occasionally, hydrogen bonds may have some quantum mechanical characteristics to them, but actually many physical chemists believe that that's almost never, that if it ever happens, it's so rare to be irrelevant. Almost all physical chemists would agree that the vast majority of hydrogen bonds are simply electrostatic interactions. Very fancy computer programs that simulate biomolecular systems treat hydrogen bonds simply as Coulombic electrostatic interactions. So the particular jargon is used to describe hydrogen bonds. There is the donor. The donor is the species that contributes the positive charge or has the hydrogen on it. The acceptor is the negatively charged species that interacts with the hydrogen. The H bond is a example of a dipolar electrostatic interaction. Again, in this case, the carbonyl group does not really have a net charge on it, but it does have a charge separation with positive charge on the carbon and negative charge on the oxygen. the water molecule similarly has no net charge, but it has a charge separation with positive charge on the 2 hydrogen atoms and a negative charge on the oxygen atom. So to understand the energy of this hydrogen bond, what we want to do is what we would do using the result derived in the previous couple slides. We will simply sum up the electrostatic potential energy of all of the charged groups here. And so, of course, electrostatic potential energy is inversely proportional to distance. So what we will do is we will approximate the energy of the interaction by looking at the closest distances. So in this case, what we would do is we will look at the distance between the hydrogen atom participating in the hydrogen bond, the hydrogen atom donor participating in the hydrogen bond, the oxygen atom. In this case, it's an oxygen atom. Of course, you can also have nitrogens as acceptors. In this case, the oxygen is an acceptor. And we will look at the electrostatic interaction between these two atoms and the atoms directly bonded to them, this carbon atom and that oxygen atom. We will ignore this hydrogen because it is yet further away, and so it is going to be smaller in magnitude, and we're going to be able to approximate then the energy of the hydrogen bond by looking at exclusively the electrostatic interaction of these 4 atoms. And why this may not be absolutely perfect, it's a very good approximation for hydrogen bonding energies. And so what we would have is, of course, the energy, E in this case represents the electrostatic potential energy of this hydrogen bond, is 1 over epsilon, the dielectric constant, delta plus of the donor, delta minus of the acceptor, these 2 atoms, over the distance of the proton from the acceptor atom, plus D plus donor, D plus acceptor. That would be the D plus donor, D plus acceptor. That would be the unfavorable electrostatic interaction between the hydrogen and the carbon up here. And then we would have the electrostatic interaction of the now the D heavy distance is this distance, and so we're looking at the electrostatic interaction of the negatively charged donor atom and the negatively charged, the negatively charged donor and the negatively charged oxygen atom bound to the hydrogen, and then the final contributor to this will be the D heavy plus DAA. We'll be looking at the the favorable interaction between the positively charged carbon atom and the negatively charged oxygen atom. So when we sum up all of these contributions, we can approximate the electrostatic potential energy of the hydrogen bond. Of course, all of these now are inversely proportional to the distances. The shortest distance here is that between the hydrogen donor and the acceptor atom. This is the smallest distance, therefore it will have the largest magnitude, and the hydrogen bonding energy is dominated by this term when the hydrogen bonding groups are in this orientation. But what will happen in solution, or some cases in macromolecules, is the alignment. This is sort of a perfectly aligned hydrogen bond. In this case, these distances, distances is much shorter than the others, and these terms can effectively almost be ignored. But now, as we get hydrogen bonds that have less perfect alignment, which would happen, let's say, if this, let's say we keep the oxygen here, but we start rotating the carbon atom in this direction. At this point, the positively charged carbon atom would begin to become closer, start getting closer to the positively charged hydrogen atom, and that would be a negative electrostatic potential, and the energy of this would get worse. So actually, for calculations that are done on, let's say, protein structures or organic molecule structures, you can actually approximate the hydrogen bonding energy based on the distance of the donor to acceptor, and then this angle of tilt of the acceptor atoms, the covalently bonded atoms in the acceptor relative to the vector between the hydrogen atom and the acceptor atom. And so this is something that's useful to know, that based on just this distance and this angle, you can get a reasonably decent approximation of the hydrogen bonding energy. So this is another, let's say, more specific example The electrostatic potential energy in general, of course, is an example of the first law, the nitty-gritty of the first law, of exactly how heat equals work equals enthalpy. So this is one example of electrostatic potential energy. This kind of electrostatic potential energy is called this hydrogen bonding energy. So again, another example of a specific kind of energy, enthalpy, that makes important contributions in biological and biochemical systems. Now, of course, when we go into bulk water, what we will see is we will not have a single hydrogen and single water molecule. It will not be standing still, as it were, in its fixed geometry. In liquid water, it will be moving around. It won't be standing still in a fixed geometry relative to some dissolved species. But what you will see in water solution, you will tend to get networks of hydrogen bonding interactions. So it's not like you would go into, of course, in ice, you find very stable hydrogen bonding interactions because that's a solid. It's a crystalline form of water. You would find precise geometric arrangement in the crystal lattice and very with very minimally varying distances between hydrogen atoms and oxygen atoms. So in ice, the angles and the distances would all be pretty much fixed. In water, of course, it's a liquid. Everything is moving around. But what you will see in liquid water is you will tend to get networks of interactions transiently over some time period. So you will tend to get, again, networks of hydrogen bonding interactions that will persist for some period of time. They won't be there all the time. Not every interaction will be favorable, but there will be a tendency to have more favorable interactions. We'll talk later about how at lower temperature these things tend to be more prevalent and longer lasting, and at higher temperature they tend to be less prevalent and less long lasting, and that's an incredibly important part of the thermodynamics of things that go on in water. That makes a very important contribution to biochemical thermodynamics and to processes like protein folding, and we'll talk about that down the line. Okay, so now we're going to go on to another example of the first law in action. In this case, and this is another example of the electrostatic potential energy in action. What this is supposed to schematize are two polarizable, uncharged but polarizable atoms that are close to one another in space. So let's say we start off with two neutral atoms, let's say just two carbon atoms, or let's say two methane molecules. Actually, in computational simulations of carbon, they tend to sort of ignore the protons because they are small and symmetrical. So actually, in fancy computer simulations of proteins, the protons are actually ignored in sort of pseudo-atoms consisting of carbon with the bonded protons are actually what is included in the calculation. So we could imagine this to be just pseudo-atoms representing, let's say, two methane molecules, or it could be, let's say, literally two argon atoms, which are single atoms. Both of these species are polarizable. And so what you will see, well, what will happen is that transiently the electron cloud in one of these atoms will, let's say, get a bit of a displacement, so that transiently you get a separation of the charges, of charge, right? So let's say just transiently the electron cloud in this atom, let's say for some moment, the electron cloud in this atom tends to be concentrated, let's say more down, right? The electrons just, let's say they move, right? Just for some little moment in time, the electron cloud tends to be polarized sort of in this direction. Well, at that point, there will be a net accumulation of negative charge in this region of the atom, and that means there'll be a net accumulation of positive charge in the opposite sort of pole of the atom. And what this will tend to do is then induce a compensating charge separation in any nearby atom that's polarizable, right? So if you accumulate transiently negative charge down here, it will tend to push the electrons away and therefore produce an accumulation of negative charge up here in the nearby atom. That, of course, negative charge accumulation will now interact favorably with this positive charge. Conversely, once these electrons are pushed away, the negative charge accumulation down here will interact favorably with the positive charge accumulation down here. So this seems a little exotic, But this is what a van der Waals force is. It is a transient electrostatic polarization or fluctuating dipole in one polarizable atom, inducing a complementary polarization in another. And so this is yet another, somewhat more complicated, but another example of the electrostatic potential energy, electrostatic forces, that's incredibly important in atomic and molecular physics and in biochemistry and biophysics, because pretty much all atoms are polarizable to some extent, and carbon atoms, hydrocarbons even, even though they don't have very strong fixed dipoles, they are polarizable. And because all atoms are polarizable, although the magnitude of the electrostatic interactions typically in these fluctuating dipolar interactions is smaller than that of the kind of fixed dipole interaction we saw with the hydrogen bond, although this is a somewhat weaker interaction in general, all atoms will make this kind of interaction, whereas only dipolar species with fixed dipoles will make hydrogen bonds. In other kinds of dipolar interactions, all atoms are polarizable, and so all atoms can participate in these kind of fluctuating dipoles or van der Waals interactions. Now, again, this interaction is called the van der Waals force. You've probably heard that. You can, historically, this has been studied in many, many different ways. It looks like somewhat of a Byzantine phenomenon at first glance, that a force that sort of occurs because of transient polarization of electron cloud. How consistent could that be? How important is that? How prevalent is it? Well, early in the history of atomic physics, people started shooting atoms around in vacuums. And even very early on, and this technology has developed now over the course of basically about a century. Mass spectrometry comes, and other kinds of important methods come from this technology involving shooting atoms around in a vacuum. Even in the earliest phase of this experimentation, which was probably really over 100 years ago, they could see that atoms being shot around in a vacuum had a strong tendency to stick to one another, even when they did not carry a net electrostatic charge. And so this was somewhat mystifying. There was a long series of sort of discussions among physicists at the time about what's going on here. Eventually, it became clear that atoms, when you bring them anywhere near one another, will tend to induce these kinds of transient electrostatic polarizations, and that these fluctuating dipoles produce rather strong forces in the end between atoms, even uncharged atoms. And so using those kinds of molecular beam methods and in other ways, you can actually sort of measure the strength of the electrostatic potential energy or the electrostatic interaction between two atoms as a function of distance. And what you see is when the atoms are infinitely far away, right? So if we move this atom all the way out to infinity, down here and beyond, it would not interact significantly. The electrostatic force always is attenuated by the square of distance, and electrostatic potential energy is always attenuated by the first power of distance. If you move them far enough apart, they will not have a significant interaction energy. So that's what's schematized here. If you move the two atoms far apart, the interaction energy is negligible. As you bring them close together, what you see is you get a negative energy, right? That means that basically that there's some force pulling them together. As the force pulls them together, electrostatic energy is released. The electrostatic energy goes to a lower or negative value. At some distance, which is called the van der Waals radius, this increasingly favorable electrostatic interaction will turn around, and now you get an unfavorable interaction, an electrostatic interaction. You can probably guess that comes from the overlap of the electron clouds. Or electron clouds do not like to overlap. Actually, for both electrostatic reasons, you don't like to have electrons too close to one another, and quantum mechanical reasons, the Pauli principle also contributes to this being an unfavorable kind of interaction. As you push the electron clouds together, you get unfavorable repulsive electrostatic interactions. The electrostatic potential energy goes first to zero and then goes up. This minimum point, we have the most favorable electrostatic potential energy. That is called the van der Waals contact distance. The van der Waals contact distance would be the distance shown here between the centers of the two atoms. The van der Waals radius is basically half of that contact distance, or to put it differently, the van der Waals radius here, well, the van der Waals radius, sorry, the van der Waals radius would be a radius, right? So this would be, sorry, this would be 1 van der Waals radius from the edge to the center of this atom. This would be another van der Waals radius from the center to the edge of this atom. The sum of the two van der Waals radii would be the distance between the centers of the atom, the centers of the atoms. That distance where the electrostatic potential energy is minimized, the most favorable interaction distance, that again is called the van der Waals contact distance. Half of that would be the van der Waals radius. 2 van der Waals radii equal 1 van der Waals contact distance. And then this minimum energy would be called the van der Waals interaction energy. Now, it turns out that you can parameterize this energetic dependency by a polynomial. This is this equation does not come from some sort of deep quantum mechanical analysis or deep physical model. This is simply comes from people having, through molecular beam experiments and other means, having measured the electrostatic interaction energy as a function of the separation between two atoms. This simple polynomial describes effectively the shape that you see here. When the distance between the two atoms is d van der Waals, of course you would have d van der Waals over d van der Waals 1 to the 12th. And this would also at that distance be 1 to the 6th. Of course, 1 to the 12th is 1 and 1 to the 6th is 1, so it's 1 minus 2, negative 1. When d equals d van der Waals, the interaction energy is negative e van der Waals. So again, that's the most favorable or the minimum electrostatic interaction energy between them. If you look at how this equation will behave, when you go to distances below d van der Waals, the value of this will be, the ratio, of course, will be greater than 1. And so you'll have a positive term that will be something greater than 1 to the 12th power minus 2 times a negative term that is something a little bit over 1 to the 6th power. Well, obviously, the 12th power is, if the ratio is greater than 1, the 12th power dominates the 6th power, and you get this the positive interaction energy or repulsive the positive energy, the unfavorable interaction energy, the repulsive terms dominate as you go up to positive energy. If, on the other hand, d is greater than d van der Waals, we go out here, what you see is, at that point, you have a quantity less than 1. If you raise a quantity less than 1 to the 12th power, that will be smaller in magnitude than the same quantity raised to the 6th power. And so in that regime, the negative term dominates, and you get net favorable electrostatic interaction energy. So again, this is a empirical parameterization. You can express it as a mathematical equation, but again, this equation does not come from any sort of fundamental physics, at least not analytically. It is simply an empirical polynomial description of the energetic profile you get from this kind of van der Waals force as two atoms of any type approach one another. Now, the strength of van der Waals interactions between different atoms varies, but basically any two atoms will have some van der Waals interaction between them that will have a functional form that roughly resembles this. For different kinds of atoms, the magnitude of E van der Waals and the magnitudes of the van der Waals radius will differ. But all of them will have a energetic profile that looks something like this, where the electrostatic interaction energy becomes more favorable as they come together. And again, that's because of the favorable electrostatic interaction between the transient. Sorry, I'm going to move back here a moment. Right, so this is negative here, means favorable electrostatic interaction energy, and that's because of the favorable electrostatic interactions between these induced dipoles. It's because the dipole in one atom induces a complementary dipole in the other atom, where you have favorable electrostatic interactions between the dipoles. Okay, and so this is an description of what is called the van der Waals force. It is weaker than the hydrogen bond, but it is pervasive, right? It's only certain atoms in proteins, in aqueous solutions. Well, water atoms all hydrogen bond, but things that you dissolve in water, different biological, biochemical species, organic compounds, some of them H bond and some of them do not, but all atoms make van der Waals interactions. And so therefore, although the van der Waals interaction is weaker than the hydrogen bond, it is pervasive. And because all atoms do this, it does in aggregate make a very significant contribution to biological and biochemical energetics. This force is most commonly called the van der Waals force, but it's also called the 612 force in some cases, in some places rather. That comes simply from these exponents in this polynomial that empirically describes the shape of the force as a function of distance. It's also called a London force. That's because there was a famous conference among physicists in London where they came to agree on what this mysterious force was that was pulling neutrally charged atoms together. Again, this is very easy to measure if you have physical instrumentation with any degree of sophistication. But when it was first measured, it was quite mysterious about what was causing it, and took humans a while to figure out that it was coming from some kind of, again, fluctuating or transient complementary dipole phenomenon. It's also called the dispersion force because effectively the charge separation in one atom produces a dispersion or separation of charge in the other atoms. Okay, and so this is yet, guess what, another example of the first law of thermodynamics in action, another specific way where heat it can be equal to work and is equal to enthalpy. This kind of enthalpy is called van der Waals energy. Okay, now we're going to consider next, and the final thing we'll do for this segment of the in this screencast, we'll consider how the van der Waals interaction energy changes when, rather than having two polarizable atoms interacting with another, we have instead a atom with a fixed dipole, like a water molecule, interacting with a polarizable atom. You might imagine, and it is true, that the fixed dipole is more effective at polarizing the charge in the nearby atom. And so the fixed dipole in water will, again, if this were just another polarizable atom, a transiently fluctuating dipole here will induce a complementary dipole in a nearby polarizable atom. If you have a fixed dipole, as you do in a water molecule, that is more effective in introducing the complementary dipole, and therefore it more stably induces this charge separation. And basically, therefore, because this is not fluctuating and not transient, you get a stronger, basically, interaction between the fixed dipole and the complementary charge in the polarizable atom. And so the fixed dipole in a water molecule induces a complementary transient polarization in a nearby atom. This is, again, a similar phenomenon to the van der Waals, that what produces a van der Waals force. This is a kind of van der Waals force. It is a stronger kind of van der Waals force. So when you have a fixed dipole as in a water molecule that's participating in a van der Waals interaction, because this dipole is stable in time, it does induce it is more effective in inducing the compensatory charge separation in the nearby atom, and you get a stronger kind of van der Waals interaction. And so, sorry about that. And so this kind of stronger van der Waals interaction that happens when a polarizable atom interacts with a fixed dipole, this is an extremely important interaction in biochemistry and biophysics, in biology. Why? Well, because life is a water-based phenomenon. Human cells, all cells on this planet have evolved in an aqueous medium. Biochemistry takes place in water. biophysics takes place in water. Proteins and DNA are present in water. They interact in water. Life is a water-based phenomenon. Water, of course, has a fixed dipole. Water, therefore, has very strong van der Waals interactions with polarizable atoms. We'll see later that this kind of water interaction with apolar, or with other atoms, we call this hydrophobic hydration. I'm sorry, when the water is interacting with an apolar species, right? An apolar species, what apolar means that they do not have fixed charge separation, fatty acids, hydrocarbon, benzene, things like that, leucine side chain, these things all are apolar. They do not have fixed dipoles of significant magnitude, but they are polarizable. When they are present in water, when they are hydrated, you get these strong van der Waals forces between the water and the polarizable apolar atoms, molecules. We'll see later on that force is called a hydrophobic hydration force. We'll see it's extremely important in understanding the thermodynamic properties of macromolecules and of biological systems.